Hello and welcome to another Algebra 2 lesson by eMath Instruction. My name is Kirk Weiler and today we'll be doing Unit 10, Lesson 9 on the remainder theorem. Now this lesson directly follows from our previous lesson on polynomial division and specifically on the technique of polynomial long division. So if you haven't learned how to do polynomial long division, this is probably not the lesson that you want to be watching right now. You will pick up probably on how to do it within the lesson, but it would be really good for you to have seen our Unit 10, Lesson 8. Anyhow, let's jump right into it. A remarkable property. In the last lesson, we saw how two polynomials, when divided, often resulted in another polynomial and a remainder. The remainder has a remarkable property in certain types of division, and we're going to play around with that in the first problem. Now, one thing I would suggest you having is your graphing calculator available. I'll be working with the TI Inspire, and that's going to help us quickly evaluate certain polynomials for particular values of x. Anyhow, let's jump right into exercise number 1. Consider each of the following scenarios where we have p of x divided by x minus a. In each case, write the quotient in the form q of x plus r divided by x minus a, that's what's known as the quotient remainder form, using polynomial long division, and then evaluate p of a. All right, so in other words, regardless, I want to think of each one of these things as being some polynomial divided by x minus some integer. All right, so let's take a look at letter A. Here I have x squared minus 8x plus 18 divided by x minus 2. All right, so in other words, I have the polynomial x squared plus 8x minus 18 all divided by the linear factor x minus 2. Let's take a look at what we get when we write this in what's known as quotient remainder form, and this will be a good review of how we do polynomial long division. Let's jump into it right now. All right, here we go. So I'm going to take x squared minus 8x plus 18, and I'm going to divide by x minus 2. And let's kind of take a look and come off the board, and I'll walk you through it again. Remember, I'm going to take this x and that x squared, and I'm going to just match them up. Now, in order to get an x squared, I'm going to multiply that x simply by x, and then I do x times x minus 2, which is x squared minus 2x. Now, like all long division, what I now want to do is subtract x squared minus 2x from x squared minus 8x. My tip from the last lesson is instead of subtracting this, what I'm going to do is I'm going to change the sign on both of them and add instead. The x squareds cancel, I get negative 8x plus 2x is negative 6x. I drop the 18 down, right? Now I say to myself, what do I have to do to get the negative 6x to be eliminated? I'll have to multiply that x by negative 6. So I want to match those, negative 6x plus 12. Again, I'm going to just change my signs and add. So those two cancel. 18 plus negative 12 is 6. And so all of this then is equal to x minus 6 plus 6 over x minus 2. So that is my quotient remainder form. In other words, when I divide a polynomial by a polynomial of a lower degree, that's important, a polynomial of a higher degree by a polynomial of a lower degree, I get another polynomial plus some constant, or it could be minus if that constant's negative, plus some constant divided by whatever I was dividing by. This is exactly analogous to taking something like 13 and dividing it by 5 and getting 2 plus 3/5, right? So 5 goes into 13 two times with a remainder of 3 left over. So 13 divided by 5 is 2 3/5. X squared minus 8x plus 18 divided by x minus 2 is x minus 6 plus a remainder of 6 divided by x minus 2. Now what we're talking about today is what's called the remainder theorem. And what I'd like to now do is I'd like to take that polynomial and evaluate it at x equals 2. Notice what I'm doing is I'm evaluating it at the zero indicated by that denominator. So I'm not evaluating it at negative 2, I'm evaluating it at 2. So let's just use our calculator for that. That's going to be very easy to do. I can just take my calculator out, right? I'll take 2 and I'll store it in x. And now let me just type that polynomial in. X squared minus 8x plus 18. Oop, and p of 2 is equal to 6. All right, so great, whatever, right? So the numerator evaluated at x equals 2, the 0 that's indicated by the denominator, is equal to 6. Awesome. Okay, so let's keep doing this. We're just going to do problem after problem like this. We're going to do 4 of them. All right, what I'd like you to do is I'd like you to try letter B, both write this in quotient remainder form and also evaluate p of 7. Pause the video now and go ahead and go through that. All right, let's do it. I'm going to just throw this over here. All right, we have x squared minus 2x minus 25. I'm going to go through this one a little bit faster, divided by x minus 7. I'm going to have x times x minus 7 is x squared minus 7x. As always, I'm going to negate and add, cancel. That's going to be 5x minus 25. That's going to be plus 5. That'll be 5x minus 35. Negate and add, that's going to give me 10. So all of this is equal to x plus 5 plus 10 divided by x minus 7. All right, so that's step 1. Step 2, again, I'm going to take the polynomial that's in the numerator and I'm going to evaluate it at the 0 of the denominator. So the 0 of x minus 7 is 7. All right, and again, let's just kind of take a look at this one really quick. Let's bring this thing up. I'm going to take 7, store it in x, and I'm going to get x squared minus 2x minus 25. And I get 10. So p of 7 is equal to 10. Now, you might already be getting a feeling that something strange is going on here. Let's keep going. So now I've got a couple where instead of having an x minus, I have an x plus. Now that doesn't change anything in terms of the polynomial long division, but keep in mind that the 0 that I'm going to be evaluating that numerator at is not x equals 3, but x equals negative 3. So I'd like you to pause the video again, and I'd like you to do this polynomial long division, and then evaluate the polynomial when x is equal to negative 3. Pause the video now and go ahead and do that. All right, let's go through it. So we have 2x squared plus 11x plus 11, love it, divided by x plus 3. To match those up, I'll have a 2x here. That'll be 2x squared plus 6x. Negate and add, those cancel. 11x plus negative 6x is 5x plus 11. Then I'll have plus 5 here. That'll give me 5x plus 15. Again, negate and add. 11 plus negative 15 is negative 4. So all of this is going to be 2x plus 5. And then it's typically written as plus negative 4 divided by x plus 3. Or you could write it as minus 4 divided by x plus 3. Either way. Now, if you did that all correctly or not, if you evaluate p of negative 3, what you end up finding is that p of negative 3 is equal to negative 4. Okay, let's do one more. Letter D. Here we have 3x squared plus 7x minus 20 divided by x plus 4. We want to write that in quotient remainder form. And we want to evaluate the numerator when x is equal to negative 4, the 0 of the denominator. So pause the video now, see if you can get through the polynomial long division, and also evaluate p at x equals negative 4. Pause the video now. Okay, let's do it. So here we go. One more polynomial long division. If you didn't get enough practice on last night's homework, here hopefully you're getting enough. Here we have a 3x giving me a 3x squared plus 12x. Again, negate and add. Those cancel. 7x plus negative 12x is negative 5x minus 20. I'll put a negative 5 here. That'll give me negative 5x minus 20. Oh, I like ones that look like that because I negate and add and I have a remainder of 0. So all of this is 3x minus 5. And just to be very succinct, you know, even though it's a little bit weird to write it this way, given that the remainder is 0, I'll have 0 divided by x plus 4. And if I evaluate p of negative 4, I get 0. So what's going on here? In letter D, my remainder was 0, and p of negative 4 was 0. In letter C, I had a remainder of negative 4, and p of negative 3 was negative 4. In B, right, I had a remainder of 10, and p of 7 was equal to 10. And in letter A, I had a remainder of 6, and p of 2 was equal to 6. It appears, right, that the remainder that I get from polynomial long division, specifically division by something that looks like x minus a, will always be whatever the polynomial in the numerator is evaluated at the 0 of the denominator, evaluated at x equals a. And that, in fact, is true and what is known as the remainder theorem. Let's take a look. The remainder theorem. When the polynomial p of x is divided by the binomial x divided by x minus a, sorry about that, then the remainder will always be p of a. In other words, p of x divided by x minus a is equal to q of x plus p of a divided by x minus a. All right, so that remainder isn't some kind of haphazard number. It is actually what you get when you evaluate the numerator at the 0 of the denominator. That's again assuming that you're dividing by something that looks like x minus a or x plus a. Doesn't work if you're dividing by x squared minus 2 or 5x minus 1. But as long as what you're dividing by is a linear factor whose leading coefficient is equal to 1, then you will always get a remainder that's equal to the polynomial in the numerator evaluated at that 0 of the denominator. So let's take a look at exercise number 2. If the ratio x squared minus 11x plus 22 divided by x minus 9 was placed in the form q of x plus r divided by x minus 9, where q of x is a linear function, then which of the following is the value of r? Well, one of the easy ways to do this problem is to simply do the polynomial long division. The other way, though, which is much faster, is to try to use the remainder theorem. Pause the video now, and whether you do it the longer version with polynomial long division or with this particular theorem, try to figure out which one of these choices is correct. All right, awesome. Well, again, the remainder theorem says that the remainder, r, has to be equal to that numerator, right, evaluated at the 0 of the denominator. So if I literally take the numerator, x squared minus 11x plus 22, and I evaluate it at x equals 9, not x equals negative 9, and you can bet they put a choice in here that represents that, but evaluated it at x equals 9, then I'm going to get the remainder. So if I just bring this out, and I could do the store, but since I already have this sitting here, 9 squared minus 11 times 9 plus 22 looks like my remainder must be equal to 4. Now, don't get me wrong, right? One other way of doing that is to literally do the division. And I can do the division quickly enough that, although I'll have red show up, if I actually did the division, it would look like this. Let me just really quickly pop through it. Negative 2x plus 22, that would be negative 2, negative 2x plus 18, negate. 22 plus negative 18 would be 4, and there would be that remainder. Okay? So either way, right, but they do want you to know this theorem, which is when you divide a polynomial by x minus a, the remainder will always be the polynomial evaluated at a. All right. Now, let's talk about factors of polynomials. In the past, the remainder theorem was actually primarily used to aid in evaluating polynomials. So it actually made the evaluation of polynomials really, really fast, especially if you learned a technique known as synthetic division, which is not within the scope of this course, but you may learn it either if your teacher decides to teach it to you in this course, or if you take pre-calculus. These days, though, it is the primary justification for determining if a linear expression is a factor of a polynomial. Now, never forget, right? If I wanted to know whether or not, let's say, 5 was a factor of 35, right? If 5 is a factor of 35, well, you might say, yes, of course 5 is a factor of 35, because 5 times 7 is 35. But better yet, 5 is a factor of 35 because when I do 35 divided by 5, I get a remainder of 0, right? On the other hand, is 5 a factor of 37? Well, the answer is no, because when I do 37 divided by 5, I get a remainder of 2, which is not 0, right? So when something is a factor of something else, it means that when you divide the two, you get a remainder equal to 0. And that's really important to understand as we now consider how to come up or how to use the remainder theorem to think about factors. So, exercise number 3. By definition, x minus a is a factor of p of x if p of x divided by x minus a is q of x, where q of x is another polynomial. What must be true about the remainder, p of a, for x minus a to be a factor of p of x? Explain. All right, so pause the video. What must be true about p of a, right, the polynomial in the numerator evaluated at the 0 of the denominator, all right, in order for that x minus a to be a factor of p of x? Pause the video now. Okay, well, p of a must be equal to 0, right? And the explanation is if p of a is equal to 0, then p of x divided by x minus a will be equal to q of x plus 0 divided by x minus a, and then that is 0, and we just get p of x divided by x minus a is equal to q of x. And again, this is very symbolic, right? So always think about it back in terms of numbers. The idea being, right, if I take 35 and I divide it by 5, I get 7. There is no remainder, right? So 5 is a factor of 35. Here, we're basically saying, look, if I take a polynomial and I divide it by x minus a and I get another polynomial, well, that's what it means for x minus a to be a factor of p of x. On the other hand, if I got q of x, a polynomial plus some non-zero remainder, well, then it's not a factor, okay? But what that means is I can tell whether or not something is a factor of a polynomial by seeing if the polynomial is equal to 0 at the value of x that is the 0 of that factor. And we've kind of used this before, right? This is sort of almost the opposite direction of the zero product law, right? The zero product law says if I know that something is a factor, then a is a 0. This now says if a is a 0, then x minus a must be a factor. Got that? So if x minus a is a factor, then p of a must be 0. And likewise, if p of a is equal to 0, then x minus a must be a factor. And that we use all the time in advanced algebra. Let's take a look in exercise number 4. Determine if each of the following linear binomials are factors of the listed polynomials by evaluating the polynomials at the appropriate value of x. All right, so, is x minus 3, in letter A, a factor of p of x equals x squared minus 11x plus 24? Okay, now one way to do that is to try to factor x squared minus 11x plus 24. But the other way to figure it out is to say, all right, well, what is P of 3? Now, kind of like doing this long ways, 3 squared minus 11 times 3 plus 24. Now again, we could totally do this on our calculator. Okay, nothing wrong with that. But we would get P of 3 is 0, because 9 minus 33 is negative 24, plus 24 is equal to 0, and the answer is yes, because P of 3 equals 0. And again, what that means, right? What that means is that I could take x squared minus 11x plus 24 and factor it as x minus 3 times some other linear factor, which is a wonderful thing to be able to figure out. One of the two factors of this. If I really wanted to know the other factor, I could take this and divide by x minus 3. Okay, take a look at letter B, right? Is x plus 5 a factor of P of x equals 2x squared plus 9x minus 2? Well, again, here, the important thing isn't to evaluate P of x at 5, but to evaluate it at negative 5. So what would I do? I would take P, evaluate it at negative 5, which again is 2 times negative 5 squared plus 9 times negative 5 minus 2. And here, I think I'm going to get a little lazy, right? I'm going to try to save a little time. I also am worried about being accurate. Let me just clear this out, right? So here, maybe I'll store negative 5 in x, and I'll type in 2x squared plus 9x minus 2. And I find that P of negative 5 is equal to 3, and then the answer is no, because P of negative 5 doesn't equal 0. All right. Now, letter A and letter B are both quadratics, right? And in theory, you could have figured out whether or not these two things were factors by simply literally factoring the two quadratics. You know how to factor quadratics. But this really becomes more helpful once we go 1 degree up. Once we get to cubics, the only way you know how to factor cubics is by grouping, and quite frankly, grouping doesn't work for the majority of cubics, right? It just doesn't. It wouldn't work on this one, it wouldn't work on that one. And yet, we can still tell if x plus 1 is a factor of this cubic and x minus 5 is a factor of that cubic by evaluating this one at negative 1 and this one at positive 5. So I'd like you to pause the video right now and see if either one of these two things are factors of those respective polynomials. All right, well, in this one, again, all I'd want to do is figure out what P of negative 1 is. We're going to save ourselves a little time. We find out actually that P of negative 1 is 0, and so the answer is yes, because P of negative 1 is 0. Okay, in letter D, we would want to evaluate P of 5, and whether we do that with our calculator or by hand, we find that's negative 5, and then the answer is no, because P of 5 doesn't equal 0. And that's it, right? Now again, the remainder theorem overall is way more complex and rich than all of this. But the primary use of it at the Algebra 2 level is basically saying, look, if I take a look at any polynomial and I evaluate it at, a 0 indicated by the binomial factor, if that remainder is 0, right, if the polynomial evaluated at the 0 of that factor is 0, then then that binomial is a factor of that polynomial. Let's try one last one. I think this last problem is kind of cool and really kind of stretches your mind in this type of problem. Exercise number 5. For what value of k will x minus 4 be a factor of x squared plus kx minus 52? Show how you arrived at your answer. All right, well, I'd like you to really kind of dig deep and think about how you can take what we were just looking at and figure out there's one value of k that will make x minus 4 a factor of that quadratic trinomial. Pause the video now and see if you can figure out the value of k. Well, so let's just kind of lay it out, right? Let's figure it out as we go. If x minus 4 is a factor of x squared plus kx minus 52, then 4 squared plus 4 times k minus 52 has to be equal to 0, right? So if x minus 4 is a factor of this polynomial, then when I take 4 and I substitute it into the polynomial, it has to be equal to 0. But the cool thing now is the only thing left there is k. So I can solve for it, right? And I can solve for it pretty easily. I get 16 plus 4k minus 52 is equal to 0. Man, red just keeps wanting to come back. I should combine the 16 and the negative 52. That will be negative 36. Yep. And now I could do 4k is equal to 36. Divide by 4 on both sides. And k will be equal to 9. All right. Awesome. Right? And kind of a cool problem. I've seen variations of this on the SAT before, right? And again, it's that connection between a factor and a 0. If this is to be a factor, then x equals 4 has to be a 0, meaning that when I substitute 4 into this expression, it must be equal to 0. All right, let's wrap this thing up. The remainder theorem is kind of a heavy theorem, right? And it's this idea that when I divide a polynomial by a very specific looking linear factor, or a linear binomial, x minus a, then I'll always get another polynomial plus a remainder divided by x minus a, where that remainder is the polynomial evaluated at the 0 indicated by that linear binomial. That's a lot. In fact, I could barely get through it just talking about it that way. The main way that the remainder theorem is used at the Algebra 2 level, though, is to justify or to figure out whether or not a particular linear binomial is a factor of a polynomial. And the cool thing is we could have a polynomial that's like x to the 5th with an x to the 4th, etc., etc., etc. And if I said is x minus 8 a factor of that thing, you would just say, well, I'll just take that polynomial, figure out what its value is when x is equal to 8, and if it's equal to 0, well then x minus 8 is a factor. And if it's not equal to 0, then x minus 8 is not a factor. And it basically just boils down to that. All right, well, we'll be using the remainder theorem, especially in that major context of whether or not something is a factor, on and off for the remainder of the course. For now, I just want to thank you for joining me for another Algebra 2 lesson by eMath Instruction. My name is Kirk Weiler, and until I see you again, keep thinking and keep solving problems.